Boa tarde a todos, pessoal. Então, sejam bem-vindos a mais uma Mock Classes. Então, hoje a gente está dando continuidade à trilha de Health and Science. Hoje é a segunda aula e será como descobrir planetas. Eu estou particularmente bastante interessado nesse tópico e a aula de hoje vai ser ministrada pelo professor Will Aldrich, da Northern Arizona University. Então, sempre lembrando que ao final da trilha tem prêmio para quem participou de pelo menos 3 aulas da trilha. Os recadinhos de hoje, não deixar de seguir o Insta da Efígie, o @efígieeduca. Então, todas as novidades vocês podem acompanhar por lá, e além de outros prêmios que a gente está programando até o fim do ano. E também seguir a Efígie nas redes sociais, no Telegram, no YouTube, e nas outras mídias sociais. Então, a gente já vai direto para a aula. So, welcome, Professor Will.
Hello. Let's see, I should share my screen here. Okay. Hi, everybody. My name is Will Oldroyd, like Eriko said, and today I'm going to be talking about how to discover a planet. So if you have any questions, feel free to ask them at the end or to put them in the chat, and I'll try to answer them as I go. If I'm talking too fast, let me know and I can slow down a little bit. And here we go. So first, here's a little bit about me. This is me, and this is my lovely wife and our son, who's 4 years old now. Some things that I enjoy doing are traveling. Here's a picture of me in Switzerland, Bern, Switzerland, next to a statue of Albert Einstein. This is where Albert Einstein lived when he made a lot of his famous discoveries and theories. Another thing I enjoy is chess and other board games. There's a nice giant chess set in a park I was playing with my wife. I love space and cool telescopes. Here's me next to the telescope where Pluto was discovered. And I like hiking. This is in southern Utah in the United States of America. And this is at Arches National Park. So it's this beautiful rock arch that I hiked to. Flagstaff, Arizona is right here in the United States. And the Grand Canyon is right here, which is this really beautiful, huge canyon, amazing natural wonder of the world here. And so, yeah, that's where I live. I don't speak Portuguese and I've never been to Brazil, but this is my wife's brother right here, and he's a missionary right now in Sao Paulo. So I know where Sao Paulo is, but I don't know where any of you are from. So go ahead if you want, put where you're from in the chat so I can kind of get an idea of where in Brazil everybody is. Campinas, that's right here. Awesome. Okay. Anyone from anywhere? Fortaleza? That's up here, right? Yeah. Okay. Oh, we got all over the place. That's cool. Awesome. Well, that's great. Okay. Yeah, so I don't speak Portuguese, but I do speak Spanish. So I can understand a little bit of Portuguese, but not really. So if you have a question and need a little bit of help, Eriko's definitely there to help if you need help with your question. Okay. So jumping into how to discover a planet. In ancient times, so before modern astronomy, there were 5 known planets, and they were Mercury, Venus, Mars, Jupiter, and Saturn. And they didn't even know that Earth was a planet then. Many of the ancient peoples didn't. And those planets were really obvious because you could see them move in the night sky. They look like stars, but they wandered around. And that's where the name planet comes from, is it means the ones that wander or move in the sky. And then in 1610, everything started to change in astronomy with Galileo. And Galileo was the first person to build a good telescope. Another one had been built before, but he built the first good telescope. And he used that telescope to look at Venus and Jupiter and Saturn, for example. And he thought the rings around Saturn were ears. He called them the ears of Saturn because he didn't know what they were. But one of the most important discoveries he made were these 4 moons of Jupiter. When he looked through the telescope, this is what he saw, were 4 little moons, and now we have much better pictures of them. And so the 4 biggest moons of Jupiter, now there are about 60 or 70 moons of Jupiter known, but these are the 4 biggest ones: Io, Europa, Ganymede, and Callisto. And so Galileo was the first person to discover something that was like a planet, a moon, using a telescope. And they were the first new things in astronomy ever, which is so exciting. And so over the next many, many years, people kept building bigger and better telescopes to explore the night sky. And so in the 1700s, William Herschel and his sister discovered the planet Uranus. And mostly they were looking for comets, and they found Uranus and thought it was a comet, but it turned out to be a planet. And so this was very exciting. There was another planet beyond Saturn. Amazing. So this one was mostly by luck that it was discovered. Then a few years later, this Italian astronomer named Giuseppe Piazzi discovered another planet. And this planet's name was Ceres. Now, you might not have heard of Ceres before because now we don't consider it a planet anymore. It's the largest asteroid in the asteroid belt. But at the time, they didn't know about any of the asteroids. And so they thought it was a planet. But Piazzi here found Ceres right before it passed behind the sun, because as everything orbits, it goes around the sun, and it passed behind the sun and was sort of lost for about 6 months until it moves out from behind the sun. And because of that, when they came back to look for Ceres, it was lost and they couldn't find it. And nobody knew where it was. And that was a problem. There was lots of debate if it was real or not, or a fake planet. And so people didn't know until this young mathematician came along, Carl Friedrich Gauss, who was 24 years old at the time. And he wanted to find this new planet again. And so he invented the math that he needed to be able to calculate where Ceres should be, where it was. And using that, they found it right away. So this was the first time that intense mathematics were used to predict where a planet would be in the future, and then used to re-find it or rediscover that planet. Then about 40 to 50 years later, these 2 astronomers here, Leverrier and Adams, looked at Uranus, and using the math that Gauss had developed, they predicted that Uranus was not moving on the orbit that it should, and that for some reason it was a little bit off. And the reason it was off, they determined, was that there was another planet beyond Uranus that was pulling Uranus slightly out of the orbit it was supposed to be in. So Leverrier called up or went over and told his friend Guy over here, who worked at the telescope, to look right there and that he would find a planet. And he did within about an hour. He immediately found this planet. And that planet was Neptune. So this was the first time that people looked at the orbits of other planets and other things in the solar system and determined that there should be a planet, another planet, because of that. And so it's predictive astronomy, predicting something's there based on what you see, even though you haven't seen the planet yet. So that was amazing. And those are the known planets that we have in our solar system so far. Just check time right now. Okay. So in the beginning of the 1900s, Percival Lowell, who lived in Flagstaff, where I am studying right now, was an astronomer, and he was looking at Neptune and at Uranus, and he thought that their orbits were a little bit off, just like how Neptune had been discovered before because Uranus's orbit was off. He thought that maybe Neptune's orbit might be off, and so there might be another planet out there. And so he hired a farm boy named Clyde Tombaugh to work at the telescope. And Clyde went to the telescope every night and observed for years and years. And even after Percival Lowell died, he was observing, looking for this other planet. And he never found the planet that Percival Lowell predicted would be there because that planet didn't really exist. The measurements in Uranus and Neptune weren't good enough to know their orbits well enough. And so he was looking at the noise in the measurements, the little bit of error based on how good they could measure was off enough that he thought there might be a planet. But because Clyde here was very persistent, he went every night and was looking for a planet, he discovered a planet. And here's the telescope he used. This is me at it again here. And there's this box on the back of the telescope. And he would take a glass plate that's this size here, and that glass plate had photographic chemicals on it. So he would put it in the back of the telescope and open up the telescope and stare at the sky. And then the light would come into the telescope and hit this glass plate. And it would change the chemicals on the plate. And then he would take it out and go develop it like an old photograph. And then he'd bring another one in, and he would do that hour after hour, night after night. And he would take two of these glass plates and put them in a special microscope. And this microscope had a switch on it. So you'd look at one plate and then flip the switch, and then it would look at the same spot on the other plate. So two pictures, and you're looking at the same spot, and he would scroll along slowly back and forth between the two. And he was looking for one little dot, like this one here. So notice these stars for a reference. There's the 1, 2, 3, 4, and there's this dot over here. And then it moved to over here on the other side of those stars. And so after years of looking, he saw this dot move about that far on one plate between 6 days apart that he took these two images. And that one little dot that moved a little bit over a few days was Pluto. And so he discovered Pluto by sheer persistence and the idea that there might be another planet out there. And we've since sent spacecraft to Pluto and found this amazing geologically active world with nitrogen glaciers shaped like a heart, and hydrocarbons and other very interesting features all over the surface of Pluto. It has ice volcanoes and sand dunes made of carbon monoxide. Very, very interesting place. But mostly he discovered Pluto through persistence. because the math didn't quite work out for Pluto. So then in the end of the 1900s, Jane Liu and Dave Jewett made another very important discovery. This is a little over 60 years after Pluto was discovered. They discovered that there were other objects out by Pluto, mostly asteroids, very large asteroids, floating around by Pluto in the outer solar system. So here is a picture of some of the orbits of, I think this outer one here is Neptune. Pluto's this yellow ring here. And then all of the other things in the outer solar system were out here beyond Pluto or near Pluto, beyond Neptune. And this was a huge discovery because it meant there was more solar system to explore. Beyond Neptune and Pluto, there were more things to discover. And so they started discovering these. Okay, and so that is what kind of brought in modern outer solar system astronomy, was this belt of objects like the asteroid belt, but more icy asteroids called the Kuiper belt. Okay. Then in 1995, there was another hugely important discovery for planets. And these were some Swiss astronomers, I believe, and they discovered the first exoplanet, the first planet around another star. And so now we're going to take a break from talking about the solar system for a minute and talk about exoplanets here. So since 1995, we've discovered over 4,000 planets around other stars, 4,000 exoplanets. It's between 4,000 and 5,000 now. I don't remember the exact number. It changes almost every day. We find new ones all the time. And this first exoplanet here, this is an illustration of it, was really, really close to the star it was orbiting. And this was really weird. It changed our idea about what the solar system should look like, or what solar systems in general look like. We'd never seen a huge planet the size of Jupiter closer to a star than Mercury. That was amazing. So the way they discovered this planet was by looking at what's called radial velocity. And this is related to the Doppler shift. If you've ever been standing on the street and you hear an ambulance drive by, as it's coming towards you, you'll hear the sound higher, doo, 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 doo. And then as it drives past you, it goes doo, 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 doo. And that's because the movement actually changes the rate of the sound waves. And that's something that we measure and see all the time. The same thing happens with light, just harder to detect. So if something is moving away from us very quickly, then it looks a little bit redder. And our eyes can't tell very well, but really sophisticated instruments on a telescope can. So if something's moving away from us, it looks redder. And if something's moving towards us, it looks bluer. And the way we measure this is by looking at a spectra, or a spectrum of the star. And a spectrum is kind of like a fingerprint for what elements, what the star or what we're looking at is made out of. And so each of these lines here, it tells us something that's in the star. Like this line might be, oh, there's hydrogen in that star. And this line might be, oh, there's lots of oxygen in that star. And so if we see the lines moved over a little bit this way, then we know it's red-shifted or moving away from us. And if we see them moved this way, then we know it's blue-shifted or moving towards us. And so you can use this fingerprint of what the star is made out of to tell which direction the star is moving, away from us or towards us. And so here is a little diagram of what happens here. So say we have this star here, and it goes in a little circle because there's a planet that's pulling on it. say this planet's really close, and so it pulls really hard. Because gravity, when things are closer, gravity's stronger than when they're far apart. So as the planet is over here, it's pulling the star. So the planet's over here, it's pulling the star closer to it. Star's coming closer to the planet. And so it wants to move kind of in a circle towards the Earth a little bit. And when the planet's on the other side, it'll pull the star towards it over there. And that will have a net effect of pulling the planet away from us. So as the planet orbits, every orbit, the star comes closer to us and then away from us a little bit. And so the light is a little bit bluer and a little bit redder every time this planet goes around the star. And you can measure that and see this little wobble here. And so those two gentlemen, those two scientists in Switzerland, measured that wobble, and based on how big the wobble was, they were able to figure out that this planet was really close and big like Jupiter. And so that was amazing. And it was a huge discovery in science and astronomy. And since then, there have been a few other ways that we have detected exoplanets. The most common way that we look for exoplanets is called a transit, or a transiting exoplanet. And so there, if you have an exoplanet that passes right across a star, you can see a little tiny dip in the light that comes from it. So we're sitting here measuring how much light is coming from the star, and then all of a sudden it goes down and then back up a little bit later. And then it's flat, and then it might go down and back up. And it'll do that every time the planet crosses the star. And a bigger planet, or a planet that's closer to the star, will have a bigger dip than a smaller planet. And so we see that and say, whoa, there's a planet there. And then we can measure how often that dip shows up. And that tells us how fast the planet's going around the star. And we can use that to measure all sorts of things about the planet. And this is actually one of the research methods that I use a little bit. There's a spacecraft called TESS, the Transiting Exoplanet Survey Satellite, and it orbits the Earth and just stares at stars for a long time. And when it sees these little dips in it, then it sends messages back to Earth saying, hey, I found an exoplanet. And so people look at that. And this is kind of what it looks like. There's all of these X's here are observations of a star. And so it sees, okay, we see a star this bright, da, 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 and then there's this little dip right here, right there, right there, right there, right there, and it comes every 6 or 7 days, or however long this is. I think this is in days. And so they see that dip every few days, and they can use that to tell, okay, there's an exoplanet there. And then what I do, I'm working with an undergraduate who's working on this project. He generates lots of different shapes that this eclipse might be. If you zoom in on this, it might look like this. And then we use a type of math called convolution. It's kind of like multiplying the two together in a special way. And that makes it so these pop out much stronger. You can see them a lot better like that. And so then we know, okay, right there, there's transits. And this is useful because see how wide this is? There's lots of noise there. And so if the transits were just barely still in the noise, this would still make them pop out of it, and we'd be able to find them even if we wouldn't be able to see these little dips here. And so that's how we discover planets that are transiting like that. And it's amazing. And that's how over 3,000 of the almost 4,500 planets discovered have been found, is through this transit method. Here is an example of one planetary system that was discovered using this transit method, and it's called TRAPPIST-1, and it's a little tiny red star with 7 Earth-like planets orbiting it. And it's amazing, and lots of people study this planet. The planets closer to the star are probably too hot for life, but maybe, and the ones far out are cold, probably too cold for life, but the ones in the middle have a decent chance of having the conditions just right for life, which is amazing. And so lots of people study this to try to figure it out. I mostly look at trying to discover the planets, and then other people look at what they're like. Another way that people discover planets is through a technique called gravitational microlensing. And this one uses Einstein's theory of general relativity, that light will bend around something that's really massive, something really heavy. And so say there's a star way over here, and we're looking at that star from Earth, and then all of a sudden this huge object, it's called a lens here, say it's a black hole, is passing in between us, in between the star and Earth. And then all of a sudden it's bending the light around it and back at Earth. And then when it passes out of view, then we see it normal again. And so, whoa, it has this cool bending effect. And it looks something like this. Basically, we were looking at the star, and then a black hole got in the way, and it smeared all of the light from the star around the outside in this ring. And you can look at the ring, and from the ring find smeared out planets around the star. And I don't do very much of this, and it's almost like magic to me how they're able to find planets in this smeared out ring. But over 100 planets have been found using this method, and it's super cool. Some of the most distant, the furthest planets away that we found have been using gravitational microlensing. And this is the last exoplanet discovery technique that I'll go over. And this is one that I do some research on. It's called direct imaging. And the idea is we have some really fancy telescope in space, and we either have a big star shade like this that's really far away that we use to block the light, kind of like holding up a piece of paper or a coin or something to block the sun. Don't recommend that. That would probably be bad for your eyes. But we block the light that way, or with a special instrument inside the telescope, and then we can see a planet orbiting that star. And so here's an example of what it might look like. They block the light from a star and then can see a planet going around that star. And this one is a very big planet. It's much bigger than Jupiter, and it's pretty far away from the star. But telescopes in the future will be able to get smaller and smaller planets that they'll be able to discover. And in the next 10 to 20 years, we should be able to take a picture of a planet like Earth around a star like the sun, which is amazing. And so what I do for my research with these planets is I try to figure out what kind of orbit they're on. Are they in a circular orbit right there? Or is the orbit tilted some way and it's going more like this? Or is it going to cross in front of the star? So I do lots of statistics and computer modeling to figure out how they're going to do that, what their orbit's going to be. Okay, so those are some of the ways that we discover planets around other stars. And that has all happened in the last 25 years that we've started discovering those. And it's amazing. Okay. So now we're going to jump back from other stars back into our own solar system and look at how we can discover a new planet in our own solar system that's farther away than Pluto. So if we jump ahead, remember in 1992 was when the first Kuiper Belt object, the first icy asteroid kind of by Pluto, was discovered. And in 2002, 10 years after that, about 20 years ago, this group of astronomers who were all at Caltech in California at the time, including Chad Trujillo, who's my advisor at Northern Arizona University, they discovered, they did this big survey and started finding things that looked a lot like Pluto. So they found Eris here, which is even maybe bigger than Pluto, and they all have fun names like Maki Maki and Haumea, Sedna. Very interesting. Some of them even have what I like to call license plate numbers. And this is just a number that's the year of when it was discovered and when during the year it was discovered. And it just is kind of a placeholder until they name the object. And this one actually has a name now. It's called Gong Gong, which is some Chinese mythology character. Anyway, so they found lots of other things that looked a lot like Pluto. And that asked the question pretty much, if there's lots of things like Pluto, are they all planets? And so they had to say, okay, is Eris the 10th planet and Maki Maki is the 11th planet? And now do we have 15, 20 planets? And so in 2006, the International Astronomical Union had a meeting, and at that meeting, they proposed to kind of draw a line somewhere else so that all of these Pluto-like objects wouldn't all have to be planets, since they are much smaller than all of the other planets and they orbit differently than all of the other planets. They're kind of on these weird tilted orbits. And so they voted here to create the dwarf planet designation. And so now these are all dwarf planets, whereas things like Jupiter or Earth are regular planets, I guess. And that was mainly because they found a lot more of them. And so they either had to make all of these planets, which they didn't quite look like the other planets, or come up with a new class, a new way to think about them. And so that's why Pluto got demoted, which was sad for a lot of people, especially people here in Flagstaff, where Pluto was discovered. But that it was to help make sense of what we saw in the solar system. Okay, so then fast forward to 2014, just a few years ago, and my advisor Chad Trujillo and his collaborator Scott Shepard here discovered another one of these Pluto-like objects. And this one still has a license plate number, 2012 VP113. Hopefully it'll have a cool name soon. I don't know when, but hopefully, because it's pretty cool. And what this object told us was that there was some pattern in the outer solar system. And so let's look at that pattern. And here's a little bit of a spoiler. This pattern is kind of like the pattern that they saw in the 1800s when they discovered Neptune. They saw Uranus was off by a little bit, and so they predicted there was another planet. So this pattern, first we're going to look at something called precession. Over a long time, lots and lots of orbits, anything orbiting the sun is going to slowly have its orbit move a little bit at a time. And for something like the Earth, you don't notice this because the Earth is almost on a perfectly circular orbit. So you hardly even notice this precession effect. It happens like every 26,000 years, we go in one orbit circle like this. And so it's over a really long time that orbits kind of slowly spin like this. But if there's something to stop it from doing this slow spin as it orbits, it's called libration. And that is kind of like a pendulum moving back and forth. And every time that it moves back and forth, it will keep a planet or an asteroid or something within a certain region. So say this blue orbit here is of a big planet. And then this pinkish orbit is of a smaller planet that's kind of trapped. And then this star in the middle is the sun. And so as we go, it'll sort of be bounced back and forth between these two sides there. And that makes it so that it stays sort of in one spot. And so when they discovered 2012 VP113, that new dwarf planet, they looked at all of the orbits of the most distant things that we've found in the outer solar system. So here's the sun right here, and here are these orbits, and they all have these really long, stretched out orbits. But most of them are pointing this direction. They're kind of aligned here, lined up. And that's because something is keeping them in this line or close to this line. Because there's very few that are off to the sides here, and those ones might not be affected as much. And so we think that the thing that's keeping these really long orbits in this line is this planet here behind it. So I put the planet behind in the picture. It's not really behind the orbits. It's like out over here somewhere. But it's keeping them in line here. Otherwise, they'd just be all over the place. So that is one of the big evidences that there's another planet in our solar system. For my research, I look at another piece of evidence that there is another planet in the solar system. And that is this gap here. So here is a plot that I made, and all of these little green dots are all of the really distant things in the outer solar system. And these big green dots are all of these asteroids on these orbits in this picture. So those are the big green dots. Now, if you look at this plot, you can see there's green dots over here, and then a couple over here, including this one, 2012 VP113, the new one. And then there, in between, there's sort of this big gap. And so that's what I was looking at and have been looking at to try to figure out, did Planet X, this new planet that we're thinking about might be there, did that planet cause this gap? And so what I did is I used NAU's supercomputer, which is called Monsoon. And a monsoon is the rainy season that we get towards the end of the summer. Anyway, Monsoon has 2,800 plus cores, and they just upgraded it. So now I think it's closer to 3,000 cores. And that's basically 3,000 computers in it, 16 GPUs, which GPUs are really good for number crunching. They're the same thing that runs video games on your laptop. The GPU is the graphics thing, but we don't play any video games on the supercomputer. They're just for computing, doing science, pretty much. It has tons of memory, tons and tons of storage, and the best part is that it's free for NAU students and faculty to use for their research. And so I have used over 1 million computing hours on Monsoon for these simulations that I'm doing to try to figure out where Planet X might be. And so what I do is I put the sun in my simulations and these giant planets here, Jupiter, Saturn, Uranus, and Neptune. And then I stick in lots and lots of test particles. So I put all these dots all over the place. And then I put Planet X somewhere in the simulation and see what all the dots do as they move. So I will run my simulation for 4.5 billion years of simulation time and see what happens. And I do hundreds of these simulations. So here, I'm going to show some videos, hopefully, of what the simulations look like. So this is what it looks like without Planet X. We've sort of got our starting particles down here, and they, Neptune pushes some of them up here, and they wiggle around, but they don't come near the gap at all. And so here is an easier to see heat map of that. So we see all of the green dots are the same green dots that we had before. Those are the real things in the outer solar system. And the big green dots are the ones that I showed that cool orbit plot for. And there's the gap. But if we don't have Planet X in our simulation, all we see is that particles go over here sometimes, and red is particles are there all the time. Blue is almost never, white is never. And so they come up here and do their thing, but they never come over here where we see things all the time in the solar system. And so that's like, maybe we need something to put particles over there. And so when we do have planet X, we get something really interesting here. Now we'll start with the same group of particles down here, and they're excited up here by Neptune, and then they fly all over the place because of planet X. So lots of them get pulled out, and then some come back in, and they kind of bounce back and forth in here. And that's really interesting. So when we look at that, oops, let's go to the next page here. Okay. So when we look at that in this heat map, we see, okay, we have some of these guys here and stuff on the other side here. So that's good. We make these things that we see. But there's also stuff in the gap. And that's a little bit of a problem. And some people have said, well, because there's stuff in the gap and we haven't really seen stuff in the gap, maybe there's no planet X. Good question, Alex. I'll get to that at the end here. So, yeah, so there's stuff in the gap in the simulation, and that's a little bit confusing. So we look at the simulations and see how much stuff is really in this gap. Is there more than these, in which case we should see it, or is there less? And so we look, and oh, this is a little bit confusing. Okay, so this green line is a histogram, one of those bar plots that shows, okay, at 45, there's 11 things at 45, and there's 0 things at 55. So this tells you how many things are at each different distance here. This is how far away stuff is in the solar system. So we've got these green dots are this big peak here in green, and these 3 green dots over here are these bumps right there. So if we look at the simulations, which are all these dotted and dashed lines here, we see that there is this big kind of gap-like thing here, and there's another gap-like dip here and a dip here. And the real particles have this gap right here, where there's sort of this dip in here, where there's nothing. But the simulations all show a few things there, but not very many. This is less than 2 here. This is 3 to 4 things. So depending on the simulation, or which planet X we put in the simulation, we get different gaps, but we do see a gap. And so that's good. It's like, okay, planet X can make a gap. Whichever planet X we put in there, we get some kind of gap thing. And based on which planet X, we might be able to find a planet X that makes the gap that we see. And so that is my goal next. That's what I'm working on right now, is trying to figure out how to, or what planet X will make this gap. And so I'm doing lots and lots more simulations to try to figure out which one works. But then also for this part, I wanted to explain why this gap was there. And this here is a plot of how long each asteroid spends in each part of the gap. So this is how long on the y-axis here. If it spends a long time in a certain area, then it'll be high up here. If it spends just a little bit of time, it'll be low down here. So these red ones are anything in the gap. So we see red is really low. Things in the gap don't spend much time in the gap. When they get to the gap, they fly through it really quickly. Things that are on the far side or the near side of the gap spend more time there. And so because these icy asteroids and dwarf planets like to spend more time not in the gap and only a little bit of time in the gap, that's why we have these gap-like features in real life and in the simulations. And so I can use that to try to figure out what gap or what planet would make a gap that looks like the real gap we see. And so that's how I am trying to predict where a planet might be. That seems a little bit more complicated than a long time ago, and they just looked, okay, the orbit's off a little bit, so there must be a planet. And that's because this planet X is so far away that it doesn't make those tiny orbital changes. You have to look at all of these really distant icy asteroids and dwarf planets to figure out what's actually going on with planet X, because planet X is so far away. For example, if the sun were the size of a soccer ball and you put it on a soccer field, the Earth would be about 25 meters away. So not too far, a little ways away. The rest of the planets would fit in about 8 soccer fields, 8 football fields. But Planet X would be probably like 20 to 30 kilometers away. It's ridiculously far away. It's just way, way out there. And because it's so far away, it makes it very hard to find. And so that's why we need to look for all of these clues. It's kind of like a mystery. Sometimes I feel like Sherlock Holmes trying to figure out all of the pieces and put them together to figure out where is this planet. And so I'm still looking for it for sure. And the way that we look for it, because it's so far away, we have to use really big telescopes. And so here is kind of a map of the sky. And all of these dots are places that we had looked as of 2018. So we've looked at a lot more places now in the past 3 years, all over the place. Yeah, we're looking at a lot of places in the sky. Haven't found it yet, but we're still looking. And we use huge telescopes like the Subaru Telescope, which is on Mauna Kea, a big mountain in Hawaii. And it is, the mirror for this telescope is over 8 meters across. And it shoots lasers at the sky, not to shoot down aliens, but to measure the turbulence in the atmosphere. If you're on an airplane, it will kind of bump up and down because of turbulence in the atmosphere. And that makes the same turbulence makes it hard to see clearly very well. And so there are a bunch of actuators or levers underneath this huge mirror that move it up and down to match the waves in the sky. And that takes out the error, and we were able to get very, very precise measurements with that. Okay, so we use that telescope. We use these two 6.5 meter Magellan telescopes in Chile. And they're on a beautiful site here. It's a snow. Yeah, gorgeous place. We use these to follow up on things that we have found with the Subaru telescope. I'll get to these questions in just a minute. They'll fit right perfect at the end, which we're really close. I've also used the dark energy camera on the 4 meter Blanco telescope, also in Chile. And I was using this telescope this last week. Unfortunately, it's pretty cloudy, so we didn't get a lot of good data, but we got some data, which is exciting. So I have to look at that still. That's really cool. And we use the Lowell Discovery Telescope, which is here right next to Flagstaff in Arizona. And it's also a 4.3 meter telescope, very big, great for this type of work. Okay, so coming here to the end, what we do with all this data is we're looking for one dot that moves just a little bit over a few nights. And those dots, usually when we find them, are these icy asteroids or dwarf planets. But the really exciting thing is that sometime one of these dots that moves just a little bit in one of our pictures, just like how Pluto was discovered, that's how we're going to discover Planet X. And so, in summary, new planets are discovered all the time. There are lots of ways to look for a planet, whether it be in another solar system or in our own. And we think there is another planet that's called Planet X, or some people call it Planet 9. I usually call it Planet X because at heart, Pluto will always be the 9th planet. And we're getting closer to finding this Planet X. So thank you so much. And now I'm ready for questions. So I'll go ahead and answer these questions that are already in the chat, and then go ahead and put more questions in the chat. I think that's probably the easiest way to go about it. Did you have anything you wanted to say here before we go into questions, Erico?
Yeah. As I have a personal question. So we're gonna have some very powerful instruments in the next couple of years, like the James Webb Telescope and another instruments. So there is any of these instruments that's for sure that they can for sure detect the planet X, and also if do you believe that we will have to wait until these instruments to start to be applying, or will you discover the planet X before that or after these instruments?
That is a great question. So, because Planet X is so far away, and this gets into what was it? Another question you had, Eriko, was that since Planet X is so far away, it gets very little light from the sun, and that makes it really hard to see. And also because it's so far away, it moves really slowly, so that these dots here, you have to wait a few days between your telescope observations to see them move. So you almost need to know where it is using something like the computer simulations that I'm doing to be able to find Planet X. The new instruments that are coming online, like the James Webb Space Telescope that'll be launched hopefully soon, is going to be very good at pointing at one spot in the sky. And so if we knew where Planet X was, for example, if we had already found it, then we'd point at that spot with the James Webb Telescope or the Hubble Space Telescope to learn more about it. But when we're looking for Planet X, these really targeted, really narrow field of view instruments that are really good at looking at one thing aren't as good for finding it. We want telescopes to have as big of a finding area as possible. So all of the telescopes I was showing have a really big area. You could fit the moon on the area that we see in the telescope more than once. They're huge. And so we use these kind of broad cone-like survey telescopes to try to find it. But then once we find it, we're going to use these amazing new next generation telescopes to zero in on it and see what it's like. To answer the next part of your question, do we think we can find it with what we have now? I think yes, and there are a few factors that we need. One, how good we can get our simulations to predict where it is. And then two, can we get lucky enough to actually find it when we look there? But in the next few years, there will be more other survey telescopes that'll look at broad areas that are better than the ones that we have now. So the longer we wait, the better we'll be able to try to find it. But I think we could find it now if, one, we do a really good job with our surveys and our simulations, and two, if we're lucky. There is a little bit of luck involved, so that's exciting. Okay, does that answer your question, Enrico?
Yes, of course. So I think we can go back to the questions in the chat. So the first one is from
Looks
Alex.
like Alex had a question. Yeah. Okay. Alex, you said, if you discover this new Planet X, what are you going to call it? And that's a good question. I actually haven't looked at naming it because I don't want to count my chickens before they hatch, so to speak. Because if someone else finds it, then they get to name it. And so I'm mostly just trying to focus on finding it, and then if I do find it, then I get to look at naming it. The International Astronomical Union, the same group of people that voted to sort of demote Pluto down to dwarf planet, have some pretty strict rules on naming planets. I think they have to be from Greek mythology and follow a couple other rules. And so there aren't that many options. And for Pluto, when it was named, actually what they did is they had a contest to see who could come up with the best name for Pluto. And it was actually I think a 10-year-old girl who was just in primary school who entered this competition and won. And so it was named Pluto after her idea. So if I discovered it, I would like to do something like that and have a big contest where people all over the world could submit ideas for what to call the planet, and then have people share in this experience. So it wouldn't, I definitely wouldn't want it to just be a cool thing for me and my research group. I would be something for the whole world to be excited about. Okay, Clara has a great question. Instead of a planet, could it be a black hole? And the answer is yes, it could be a black hole. There have been a few scientific papers that have come out about that. If it was a black hole, it would be about the size of a grapefruit or an orange. It would be this little tiny black hole. And we really don't have a way of testing for that. And so it's just an idea thrown out there. And because we don't have a way to check if it is a black hole or not before finding it, we are just focusing on the idea that it is probably a planet, because planets are more common than black holes. And we have never seen a black hole in our solar system, or a small black hole in other solar systems for that matter. And so we're focusing on the idea that it's probably a planet, but it totally could be a black hole, in which case we would never find it the way we're looking for it. But hopefully it's a planet, because then it's easier to find. If it was a black hole, people have talked about sending out a small army of tiny spacecrafts going really, really fast in every direction. But I don't think technology-wise we're quite to that point. But if you sent out this small army of spacecrafts that all talked to each other, they would be able to find it if it was a black hole.
So, Professor Real.
Excuse me, can I ask you a question?
Yes, of course.
Yes, go ahead.
Okay, so how can we discover planets out of our solar system?
Sorry, you're cutting out a little bit. I couldn't quite hear your question, Olivia.
How can we discover other planets out of our solar system? Sorry, my internet is not very good. I wrote it also on the chat, so if you can hear me, you can see on the chat as well.
Professor Real, I will also use Olivia's questions to add an additional and related question, that if we can detect really small planets, and if they have water on that, we can detect the elements that they are the outer solar planets enriched.
Yeah, that's a good question. So for discovering planets in other solar systems, what we do are those techniques that I showed a little bit earlier. And the main thing we do is by looking at stars. A lot of the time we can't see the planet itself because it's so small. We've only discovered about 50 planets by that direct imaging method that I talked about, where we look at the star, try to block out the star, and then we see the planet. All of the other planets that we found, we get by looking at the star and seeing, for example, the star wobbling a little bit, or changing color a little bit, or there being a little transit or eclipse of the star by the planet, and that's that little dip in light that we see. And so those are most of the ways that we discover other planets. You can also use some fancy math once you do discover a planet to try to find more planets around that star. And so the 4,000 to 5,000 planets that we've discovered around other stars, most of them are by looking for little dips in the light coming from the star. And several of them are from that red and blue shift that I talked about. As far as detecting water on a planet or in a planet's atmosphere, that's actually pretty difficult to do. And what you do is you look for those fingerprints. Remember I talked about the spectrum, or the lines that you see, and you see those lines move, and that's how you know if it's moving towards you or away from you. Well, those lines actually tell you what's in the star. And if you can both block out the star and get those lines for the planet, it can tell you what the planet is made out of, or the atmosphere of the planet is made out of. So a key thing that we're looking for when we can actually directly image a planet, which we'll be able to do better with those next generation space telescopes like the James Webb Space Telescope and telescopes that'll be made in the next 10 to 20 years, those ones will be able to block out the star, look at the planet, and measure how much water is in the atmosphere, for example, just based on that spectra or the fingerprint of what it's made out of, which is completely incredible that we can do that, or we'll be able to do that soon. And so what I do with those is I try to figure out the orbit as quickly as possible. I want to know if this planet is going to be too close to the star for liquid water or too far away from the star for liquid water, because it's going to take like 1,000 hours of the telescope staring at that planet just to be able to tell if there's water on it. And so if I already know that it's too close or too far away, then it's not worth spending 1,000 hours of the super advanced telescope to look at it. So I want to narrow down the possible options. So we only look at the really, really good, high likelihood of having water on them planets. Okay. Alex asked, are you taking suggestions for names of the planet? Not yet, but I will definitely let you know if and when I find it. Hopefully. There are some other groups that are working really hard to find it as well. So I don't know what they would do if they found it. But if I find it, I will let your program know for sure, and you will definitely get a chance to suggest names for it. Okay. Oh, Andrew, who is one of our contact people at Northern Arizona University, gave his email info if you're interested in looking into NAU as an option for a school and going to school.
So I will make my my final question, and if any other student wants to make this is your final chance. So would you like to know if amateurs astronomers contributed a lot in the past, but do you believe that there is still space for another amateurs discoveries, or now you need very complicated and sophisticated instruments?
So there are some things like Planet X that a small telescope, like what an amateur astronomer would have, you probably would not be able to see Planet X with a small telescope, which is unfortunate because it's really cool. But if you could see it with a small telescope, we probably already would have found it. However, there are so many cool things that amateur astronomers can do. For example, I was looking at Brazilian astronomers earlier just to look at some cool things Brazilian astronomers had done. And I found this amateur astronomer that had discovered about 200 asteroids by himself. Just new asteroids that no one else had ever discovered. And those are super cool. And they tell us a lot about how the solar system formed, like how all of the pieces came together and collided, and the different temperatures things were formed at. Is really, really interesting. And so all of the asteroids that are discovered feed into that. The coolest amateur astronomer discovery recently has been an object called I-2 Borisov, and an amateur astronomer in Russia named Borisov discovered an interstellar object, the second one ever to be found. And this object came from another solar system and was flying through our solar system. It was a comet from somewhere else in the galaxy, and it's in our solar system, and he discovered it. and it was named after him. And so that was just an amateur astronomer in his backyard, made this huge scientific discovery because he was excited about astronomy. And so it's not just a thing that professional astronomers can do. Anyone could make a discovery like this. And it's so cool.
Yeah,
One
that's
thing I love about astronomy is that it brings people together all over the world. And it basically everyone is excited about space. It's a cool thing that it sparks the imagination and makes us want to be better than we are and expand our horizons, do more as humans. And so working together on it from all tiers, from amateur astronomers to kids in school learning about astronomy to people who do it for their profession, everyone is sort of united with this excitement about space and the desire to learn more about our universe. Okay, Clara had one more question here. Do we have time to answer that, Enrico?
yes.
Okay, we're good. Okay, this is an awesome question, Clara. So do you think there can be life in Planet X or in any planet? Well, Planet X, the answer is probably not. Planet X is most likely going to be a gaseous planet, kind of like Neptune, with methane gas and ice in the atmosphere, all sorts of things that life as we know it would probably struggle. Actually, it would struggle a lot. So not super likely for Planet X, unless we discover some type of life that is completely foreign to us, which is not impossible. As far as any planet goes, I think there's definitely life on some planet somewhere other than Earth, because there are, in just our galaxy alone, there are 1 billion trillion stars. And then there are billions of galaxies across the universe, just the universe that we can see. And then there's more beyond what we can see. And every single star has, on average, more than one planet around it. And so just based on statistics, the odds are incredibly in favor of there being life somewhere. And we don't know for sure because we only have one data point so far. But I think the chances that there's life out there, very high. I don't know when or where we'll find it, but hopefully we do in the not too distant future.
Hopefully. So thank you, Clara, for your question. We just ran out of time, but it was really interesting class. So I would like to thank Professor Will as well, Andrew. So you can have Andrew contacts on the chat. So see you in the next week, guys. So bye-bye.
Thanks, everybody. Great questions. Those were awesome.
Bye, Professor.